So let's kind of walk ourselves through what we've done so far in model development. First thing we did in model development was we identified how to regress models we knew, right? We took things like kinetic parameters, we talked about simple linear equations, and we said, could we figure out how to regress it? Yeah. And the thing we learned is we have to linearize any function we want to regress. Because nonlinear regression is exceptionally complex and painful. And in reality, you generally don't have to worry about nonlinear regression because you can generally linearize your equation in some form or another. It may not be pretty, but it's going to be linearized. There are techniques if you get an equation that can't be linearized, but when you're dealing with empirical systems, you generally can just non-linearize your independent variables or your dependent variable and let that then fit into a linear equation and be done with it. So we did those regressions. We said, okay, well, how well did our model fit? We looked at residuals. We looked at the residual plot to look for shapes. We looked at R-squared values, adjusted R-squared values. Then we said, okay, well, let's look at, if we have multiple models, what do we do? How do we know which one's better? We compare adjusted R-squareds. We compared root mean squared error. Root mean squared error. We looked at the AIC and BIC. We talked about that last time. I'm going to encourage you, and we did the AIC and BIC analysis to determine which one's better. BIC, generally a better option, just because it penalizes complexity more. But again, but you take all these things together and make a decision on which model you want to use. We also looked at VIF to say, is there data? What did VIF tell us? Let me ask you that.
You see in the two variables, you see linear or not?
Right, linear meaning we have collinearity. Well, collinearity, remember we talked about said, is when two of your independent variables are not truly independent of each other. When one of them, a change in one predicts change in the other to some degree. Now, the problem is with real data, you're going to have variables that have some degree of linearity between them, very often. The key is you need to minimize that linearity as best you can. What were our thresholds in VIF for our cutoffs?
About 5 and then above 10.
Below 5 and 10.
Yeah. So below 5, you're fine. Don't even worry about it. Between 5 and 10, there could be a problem. Take a look at it. If it gets above 10, you've got to throw it out. If you have a data set where you have two variables, like the one we have here, but they're clearly the ones that are influencing each other, and we had like 6.9 and 7.0, just throw one out at that point. They're close enough, they're above 5, and one of them clearly predicts the other one very well, so just throw one of them out. If you can't figure out, like, the relationship doesn't work where it's like 1 and 4 are clearly the ones, it could often be that you have like 15 variables, and maybe you see that 3 and 5 are both multilinear, but they're not with each other. They're multilinear with a combination of the other variables. At that point, you have to throw both of them out. You just have to make that decision. So you throw one out, you do a regression. If the other one still shows multilinearity, throw it out to you, and it just makes it cleaner. You can always do that, throw a variable out, and then do the analysis and see how they behave. And that'll tell you whether you've thrown out enough of the data. Why do we do that? Well, 2 reasons. One is we want to eliminate multilinearity, because if we don't, that means that we have one variable that's having additionally weighted influence over our dependent variable. That's the example of if we do height and weight for people. If we don't get rid of weight or height, we know that being taller means you're going to be heavier by design, because we're humans, and that, like, generally if there's a significant change in height, there's a significant change in weight that goes with it. There's just going to, otherwise babies would come out like 200 pounds and, this tall, which would be creepy. Kind of fun, at least not for the mom, but fun for it'd be a cool kind of baby to play with. But you can see why that's a problem. Is you don't want undue influence from a variable unduly influencing it. So let's go back to the scenario of height and weight. How can we overcome that linearity issue?
Remove one of higher weight.
Right, we could remove one, but maybe weight's an important factor. Like, what if we're looking at how height and weight affects blood pressure? we know intuitively that weight can easily affect your blood pressure for multiple reasons. One, if you're overweight, there's likely other comorbidities that could be influencing your blood pressure. We know that if you're taller, it could take higher blood pressure for moving blood around your body. If you weigh more, it could cause restrictions on your blood vessels, which are going to increase your blood pressure. So how do we overcome that? And this is, we're going to talk a little bit about this just before we go to the next one. You may have to transform a variable to get this to work, which means you may have to pull additional information in. What if instead of throwing one out, I subtracted what the average weight for a person of that height is from the weight? What I'm doing there is I'm decoupling the variables. By subtracting that, I'm saying, hey, that portion of your weight that's expected because your height, we're going to remove that. And so instead of having weight, we have weight above average. Now that tells us we've decoupled it from the height because we've eliminated what the average weight is for a person of that height. Now, does it take into account like bone structure and all that? No. But if you do that calculation, which is something you could easily look up a value off the internet and apply it to that, you could then calculate your collinearity to, like we call it, either fraction overweight or percent overweight, or like you could normalize it. And see now if that collinearity exists anymore between the new transformed weight variable and height. Sometimes you can do that, where you can transform it to a form of the variable that eliminates that relationship. Does that make sense? You're going to probably come across examples of that in your data sets. We're going to be like, oh, this is related to that, but if I transform it this way, if I do this modification to it, I now eliminate that, at least as much as I can. We know there's still going to be some interplay in there, but we can probably get rid of most of it. And that's your goal with collinearity, is to either throw out the collinear data or transform it into something that's no longer collinear. Does that make sense to everybody? Just want to make sure. If you have questions about it, please ask, because you're going to be dealing with your data sets. So I want you to think about what this means. Okay. Cool. So with that being said, let's talk. Actually, can we think of a chemical engineering problem that would be true in? Or there might be some collinearities that we could transform like that. In what way? What variables would you write?
Temperature, pressure.
Yeah, temperature and pressure is a really good one. We know that temperature and pressure are highly correlated in a distillation column because they're directly related by volatility, right? Boiling point of the mixtures in there. So we either have to throw one out, or we need to make a statement of how can we address this differently. And maybe instead of using temperature, we back it out to a different variable. Or maybe we don't use pressure, maybe we use delta P in our column, pressure difference between our top and bottom. That may now actually be a way to introduce pressure in, but transform it in a way that will eliminate some of that relationship between temperature. Because that delta P shouldn't be a function of pressure, a function of temperature. It should only be a pressure-related issue. Okay, so as you get into your data sets and you start doing your VIL analysis, VIF analysis, you're going to discover whether all your variables are usable or not. That's what's going to come down to. You're going to decide if you're going to throw some of them out, which is perfectly valid. We're doing this because we want to make our system more robust. We want it to be predictable. We want it to be less influenced by outliers, by outliers, by leverage points. We want it to be have equal influence over linear variables, so that we're not dealing with nonlinear relationships being masked as linear because we're hiding like weight in multiple different variables, things like, or height in multiple different variables, for instance. So let's say you have 32 regression parameters, and you do the VIF and you can't eliminate any. How do we make this model smaller? We're going to look at something, and I've already talked about this a little bit, called principal component analysis. Here's called PCA. So principal component analysis is basically, I talked about this last time, is transforming the axis with which you look at your data. We're used to thinking about X, Y, and Z axes in our data. But if you have 32 independent variables, you actually have 32 axes on which your data can be plotted. The problem is we can't physically imagine 32 axes. It's not something we can visualize. We have no tools, we have no concept of how to do it. So trying to determine what is the most important axis for our data variation is impossible as far as we can do in standard thought patterns. But what we can do, so we're going to say this redefines your axes for your data. And instead of us having 32 axes, what it does is it starts to identify and say, hey, you know what? Yeah, you have 32 variables, but really your data moves aggressively this way. And this way isn't necessarily one of the 32 variables, it's some combination of certain variables together. It could be all 32 pointing in one direction, which if that happens, that's the reality of how your data falls. But in reality, it's probably gonna be like these 4 variables predict 60% of your movement. So if you just do, and it's maybe like, some codes like this, maybe it's A times X1 plus B times X2 plus C times X3 plus D times X4. If you use this relationship, we now have a new variable we're gonna call Z1, and that is your principal component 1. And that's your new axis. So you're basically manipulating your data from 4 data sets to 1 for that axis. And it goes, okay, that's cool. And you go, that's only 60%, I need more. And you go, okay, this second component will give you another 25%, and it's a combination of these. And maybe it's like 1, 2, 7, and 23. And you go, okay, cool. And then so now you're like, that's 85, we need more. It's like, okay, this third component will give you another 10% predictability, and it combines another 7 variables. Well, now I've got it basically functioning down to what looks like 3 axes. It's really like 12 or 13 variables, depending on how big these combinations are. It could be 60 variables. But I've now been able to predict 95% of my models were to predict with 95% accuracy using a subset of my data. Does that make sense? Now, the idea behind it is it's basically helping identify, and I'm going to say this in a weird way that sort of makes sense, linear subcomponents of your data. And so like we look at data and say, if I have something sloping this way, like if I have a 3-dimensional plane that's sloping this way, we say it has an X component, a Y component, and a Z component. That's sort of what we're doing here, is we're defining a new X, Y, and Z with those 3 PCAs we developed, or principal components, to then redefine our axes and say it's actually a combination of these. And then what we can do is then we can alter and calculate a new column for these new variables, and all of a sudden, instead of regressing against 30-something variables, we're regressing against 3 or 4 or 5 that are now combinations of another 12. So these calculations are done external and then fed back. It allows us to simplify the calculations and make our model more robust. Does that make sense? It's a weird theoretical concept. We're now going to talk about how you apply it. And you apply it, and I've already mentioned it, and we've been avoiding it, but now it's going to come up, using eigenvalues and eigenvectors. So what are eigenvalues and eigenvectors? Anybody remember? People remember the words, right? And you remember learning it at some point. Let me tell you what, welcome to every engineer ever. We all learned this at some point. We never used it on anything. We did a little bit in linear algebra and then it goes away. And you're never told why it's useful. So it sucks. But we're actually going to see how it's useful. Eigenvalues and eigenvectors are fundamental concepts of linear algebra. They are a basis of that. And they're used a lot in physics, engineering. Data science uses it a ton in machine learning, which is the 2 things we're talking about in here. They actually provide insight into the structure of your matrix, and they're important for matrix, what we call matrix diagonalization, stability analysis, and of course, principal component analysis, which we're going to talk about. Let's give you some definitions because they suck. Eigenvector first. It's a non-zero vector, which we're going to call V. Why do I put the arrow over the V? It's a vector. It indicates that it has a direction. Well, actually, let's go back. What is a vector? And look, and if you ever forget, how many of y'all have watched what's that? Despicable Me. There's the bad guy vector that has the squid gun. The worst and best weapon ever created. He is called vector because he has both magnitude and direction. That's actually what he says. Well, that's the definition of a vector. It has magnitude and direction. So that's the key, is it's not just a value, but it actually has a value defined in a particular direction velocity versus speed. Velocity is a vector because it says I'm moving with this magnitude in a certain direction. Speed is just a scalar. It just says I'm moving with a certain speed, 55 miles an hour. So if I run around a track and stop at 0, and I stop back at my start point, and I calculate my average speed, because my starting position hasn't changed, technically my speed would be 0. Well, actually, my vector would be 0 at that point, because I had no movement according to that. But my speed was a set value, because I went a certain speed. It's just my total movement was 0, according to spatial components. Now, if I look at any individual point along there, I had a vector at any given time. So, it is a non-zero vector that, when multiplied, by a square matrix, which we're going to A, results in a scalar which equals the matrix A times the vector V equals lambda times our vector V. What does that mean? That's a whole lot of jargon just to say it is a fundamental vector of your data matrix. The eigenvalue is the lambda that's there, and it's the scalar for magnitude of your eigenvector. Why do we care? Well, it simplifies a lot of matrix calculations. And that's what we're going to be relying on it for. Is it's going to simplify our calculations. It's used in solving systems of differential equations, which we could use it for there. It's essential for what we're doing here. And it will tell us, it allows us to create and analyze the stability, create more stability and analyze the stability of our systems. Now, let me ask you, how many of y'all remember how to do an eigenvalue or eigenvector? Yeah, that seemed what I expected, and that's perfectly fine. We're going to just relearn how to solve eigenvalues and eigenvectors because your next homework on your project is going to be determining the principal component of your data sets. The one that's, you have the one due Wednesday where you're going to be doing the VIF analysis, and you're going to be doing the QQ plots, and you're going to be applying dummy variables if you need to. The next step is, okay, you've done all that. Now we're going to do this and see how much of that data we actually need, basically. How can we simplify our regression? So let's do an example. You're given a matrix, A, that has the form 4, 2, 1, 3. So it's a square matrix. Has to be a square matrix, right? Now, the definition, or I say definition, the defining equation that allows you to calculate your eigenvector or eigenvalues is this. The determinant of A minus lambda I, I'm just gonna put those in brackets, is equal to 0. This is always true when you're doing a comparison of a square matrix and determining the eigenvector, the eigenvalue. What is I? Anybody remember that?
And
It's your identity matrix.
one more.
So the identity matrix is that guy. So this should be DET, not DEL, sorry, determinant. So if we were to write this out, it would be our A matrix, 4, 2, 1, 3, minus a scalar times a matrix, just multiplies all the components in the matrix by the scalar. So your eigenvalue is a scalar, so it's lambda times I, so it just ends up being lambda, 0, 0, lambda. And this equals 0. Subtracting matrices, I'm sorry, we need the determinant of all this. Determinant. How do I subtract these? Do you remember? You just, if you're subtracting matrices and they're equivalent size matrices like this, you just subtract the components. So it becomes the determinant of 4 minus lambda, 2 minus 0, 1 minus 0, 3 minus lambda, which equals the determinant of 4 minus lambda, 2, 1, 3 minus lambda. So what ends up happening is you just end up adding, you just subtract lambda from your diagonal. That's always how it works. This is how you get there, but from now on you can just say, oh, I need to do this, I just do 4 minus lambda, 3 minus lambda. If this was a 3 by 3, you'd have 4 minus lambda, 3 minus lambda, then whatever's down here, minus lambda. It's just subtracting because you're always multiplying it by the identity matrix. This has a 1 on your diagonal. It's called the identity matrix because it's identifying a single step along every possible axis in your matrix. Now, do y'all remember how to do a determinant?
Cross multiply.
Yep. So, in this case, it's going to be, so I'll draw it. This times this minus this times this. If it were 3 by 3, so if you had A, B, C, D, E, F, G, H, I, you'd go, so if I can do this, this, and this. So those multiplied minus this. So you basically just keep doing diagonals all the way around, that way. It's a big ugly mess to do. But with the 2 by 2, it's relatively easy. We are going to have some homework where you're going to have to do this. I apologize, but it just takes practice doing the determinants a few times. Not like a ton of homeworks, just like I do probably a 2 by 2, a 3 by 3, and a 4 by 4, so you can get comfortable. Once you get the pattern down, it's easy to do. It's just getting comfortable doing it once. So the determinant is 4 minus lambda times 3 minus lambda, then minus 2 times 1, so minus 2. Or let's go ahead and put both 1 and 2 here so you can see them. And remember, this has to equal 0. So now we just solve it. 4 times 3 is 12. 4 times minus lambda is minus 4. 3 times minus lambda is minus 3. So that's 12 minus 7 lambda plus lambda squared. Yep, minus 2 equals 0. So now let's just reorder this so that we have it in standard form of a quadratic. Our lambda squared is positive, so we're going to go out here. We have lambda squared minus 7 lambda. 12 minus 2 is 10. So plus 10 equals 0. And then we solve it. How do we solve it? No, go on. Yeah, we can factor this thing out, right? So we have lambda, we need to make minus 7 in the middle here. So we can have minus 5, minus 2. So that'll give us minus 7, that'll give us a positive 10 here. So that means our lambda equals 5. So lambda 1 equals 5, lambda 2 equals 2. What if I couldn't factor it? Negative b plus or minus the square root of b squared over, minus 4ac over 2a. Sound familiar? You can always throw it in that. Get to the same answers. Now, this is great for second order. What if it's not second order? What if it's third order? Or fourth order? Or God forbid, which is going to be a very real possibility, what if it's like 23rd order? You got to use a solver. There's the only way to do it. And you got to try multiple guesses to find all your eigenvalues. So you put it in Excel, you'll get your massive equation, and you're going to say solve for lambda by setting this equation equal to 0. And you're going to give it a guess value, it's going to find it, and then you're going to just keep trying pieces and try to find all your roots. There's really not a good way to do it. There might be a higher order root finder. I don't know what it is. What's that? You could graph it. The problem is that's assuming.
Can you graph it on Nesmo or something? You see,
What's that?
can you graph it on Nesmo? Just throw the whole function in, graph it on Nesmo.
You probably could, yeah. So instead of calling this 0, you could say lambda equals y, do y versus x, plot it, look for your intercepts.
Yeah.
Now, it's not, now the problem is if you're graphing it, reading a graph is hard. So what I would recommend is you graph it, it'll tell you roughly where those are, and then I'd use solver to find, like, I think it's 2.1. So I'm gonna say, give me 2.1, and go, and it'll then solve it, like should solve to that one. But yeah, so use a graphical method, identify your range, and then use your solver to refine it. It should work. Now the challenge is, with all of these, you're not gonna get an exact root, because you're solving a like this one was easy, this one factored. Ones that don't factor, they're gonna be like, so especially the higher order they get, these decimals are gonna get longer and longer and longer. You're not gonna carry 40 decimal places. That's insane. So you're still gonna be making approximations, but that's part of the error in any empirical form function. Now, how do we get our eigenvectors? So we've got our two eigenvalues, right? Lambda 1 and lambda 2. What we don't have is our actual eigenvectors, our V's. But what's nice about it is eigenvectors are real easy to find once you know eigenvalues. We're looking for V1 that has the form x1, y1. And we're looking for V2, which has the form x2, y2. So we're going to go back to this matrix here, and we're going to solve it. So let's start with our lambda is 5. So we say A minus lambda I equals 4 minus lambda, 2, 1 minus 1, and 3 minus lambda. And now what we're going to do is we're going to say, okay, if lambda is 5, gonna solve this and we get 1, 2, 1, negative 2. Oh, sorry, negative 1. Now, technically, these are my combinations of x's and y's. But what do you notice about this and this? You're good? Sure. This one isn't independent of this, right? This is just this multiplied by negative 2. There's actually only one vector represented here. You see that? So we're going to pull this top row, and this is our x, this is our y functionally. I mean, not functionally, it is. So we're going to have minus 1x plus 2y equals 0. That's the vector that is coming out here. Because, or I could put 1x minus 2y equals 0, and that'd be acceptable. Because that's the second row here, right? Sorry, I had this backwards, I should say. X. They're linearly dependent, we can see that here, because if I multiply this one by negative 1, I get this one. They're basically just a scalar derivative of one or the other. So we're going to pick this guy because it's there. And that's going to equate to negative x equals negative 2y, or x equals 2y. Now what's nice about this? This is a vector, right? I mean, it's not a scalar, right? Because it depends on your, like, it just says that if I choose an x, I know the y, but it is a line, which is by definition a vector. Now, how do we solve this into a vector form? Because right now, we have variables in there. Well, we just pick a value. Because this equation is true for any y and any x. Any y, sorry, there's an infinite number of y's and x combinations that this is true for. And so we're going to pick an easy one. We're going to say, because I want to deal with whole numbers, I'm going to say assume y equals 1. If y equals 1, what is my x? Yep. So congratulations, you found that vector 1 is 2, 1. Done.
When you use the bottom one, you have the top one.
If you use the bottom one, you're getting the same answer too. Oh, it doesn't matter. I used the top one and then rearranged it. But if I use the bottom one, you get to the same equation. And that's the key, is that's gonna happen. You're just defining a vector for which to define your matrix by, that's all. You could have chosen, I chose y equals 1 because I don't want to deal with decimals here. I could have chosen y equals 2 and had 2, 4. I could have chose x equals 1 and had y equals a half. That's perfectly valid. It's just defining an xy combination that defines your vector. And that's all we're doing with that. We just choose the simplest one, which is pick a y or x that gives you simple numbers in there. That's it. Does that make sense? Once you have the eigenvalue, the eigenvector becomes very easy. The eigenvalues are the hard part. Okay, so let's go ahead and do the second one. So this is all for lambda equals 5. That's the key, is what we're looking at here. For lambda equals 2, which remember is our, so this is our lambda 1. So we're going to say lambda 1 is 5, lambda 2 is 2. So this is our eigenvector to go with that lambda. We go through the same exercise. A minus lambda I equals our A matrix. So remember, this is what our lambda I looks like. Our A minus lambda I, that's U minus that equals. still looks like this because that doesn't change, so still 4 minus lambda, 2, 1, 3 minus lambda. But now the difference is we're going to introduce our value for lambda, so it's actually going to be a minus 2i. So I need to move that down, so that's out of the way. A minus 2i equals 4 minus 2, 2, 1, and then 3 minus 2. So we just insert our lambda in there. And remember, we still need to solve all this. So if we look here, what we have is 2, 2, 1, 1. Remember, x and y. These two vectors are not only are they dependent, they're identical. Did I do that backwards? No, that's right. No, I did do it. Sorry. I had it the first time. Yeah, x, y. There. Why did I do that? So, yeah. But either way, these are identical. Right? They're the same vector. So I pull this out and I can say I can either do 2x plus 2y equals 0, or I can do x plus y equals 0, but they're the same. Same vector. So then what do I do? Yeah, I'm just gonna choose a value for y or x, either one. So let's say y equals 1, because again, I'm lazy. I put y equals 1, what does my x have to equal? -1. Vector 2 equals -1, oops. -1 and 1. Solve. That's how you get eigenvectors and eigenvalues and eigenvectors. Think you can do this? Well, let's do an example. Let's have you guys work an example problem. Take about 10 minutes to do it, and then we're going to solve it. You may want Excel to do this. And I'm going to pull up Excel, and we'll work through it in Excel so you guys can see it. And we're going to make a slightly larger one. We're going to actually go to 3 by 3. And if you can get to 3 by 3, then the homework's going to get easy. Because once you get to 3 by 3, then going to 4 by 4, so forth, doesn't change anything for you. So let's say you have an A matrix defined as, it's a 3 by 3 square matrix, 6, 2, 1, 2, 3, 1, and 1, 1, 1. Fine. Lambda 1, lambda 2, lambda 3, vector 1, eigenvector 1, eigenvector 2, and eigenvector 3. I'm going to get Excel pulled up to work on this. so let's start working through the determinant, because it's a lot on this one. So, first thing we have to do is we have to subtract lambda from our diagonal. So we have 6 minus lambda, 2, 1, 2, 3 minus lambda, 1, 1, 1, 1. Now, you can do this, which should work. There's two ways to do this. So we're gonna lay out both of them and we're gonna look at like which one is gonna be easier to solve. So first one is we're gonna do all the diagonals this way, subtract it, and then subtract the time, multiply the diagonals this way, subtract the diagonals this way. So first diagonal is this one right here. So it's 6 minus lambda times 3 minus lambda times 1. Then our next diagonal is 2, 1, 1 right here. Yeah. So yeah, 2 times 1 times 1, which is 2. And put this piece in brackets so we don't lose it. And then of course we have 1 times 2 times 1, so another 2. That adds up with a 4. Let me try to screw this up because I think I am. Oh. Minus lambda, that's why. Forgot to put that in. Let me fix that. Looks like something's missing. 1 minus lambda. So that's the first diagonal. Then we're gonna multiply the second diagonal, which is 2 times 1 times 1, which is 2. We're gonna do the third diagonal, which is 1 times 2 times 1, which is also 2. So that gives us all the diagonals in this direction. Does that make sense? So we go here, here, here. So imagine if you just wrote, I think I saw somebody doing this. You just expanded this out and said, okay, I'm gonna put a 6 minus lambda piece here, I'm gonna put a 2 here. I'm gonna basically just repeat the matrix over here. The first 2 rows at least. 1, 1. So then I go diagonal, diagonal, diagonal. It allows you to see it a little easier. And so that gives us 6 minus lambda, 3 minus lambda, 1 minus lambda, 2, 2. Then I need to subtract the other diagonals. So let's switch to green for this. And we're going to subtract this, this, and that. So that's 1, 3 minus lambda, 1, 1, 1, 6 minus lambda, 1, 1, 6 minus lambda. And what's left? 1 minus lambda, 2, 2. Big ugly thing. So let's simplify this as best we can. Let's go to black so that I'm not confusing colors. We end up with 6 minus lambda, 3 minus lambda, 1 minus lambda, 4 minus, okay, so let's bring all these out here. 6 minus lambda, 3 minus lambda, 1 minus lambda. So I'm bringing all my lambda pieces forward. And I have 1, 1, 1, 1, 2, 2, 4. That can't be right. 'Cause that seems bad.
It's supposed to be a plus.
What's that? What did I screw up here?
Cross product plus.
Oh yeah, plus, sorry. This is why I don't do it this way ever. And I'm sorry, this is what's causing me confusion. Let me show you the way I do it, because this makes sense to me. Start with this guy. When you start with this guy, neglect those and just use this. So it becomes 6 minus lambda, then times the determinant of that, which is, this is why I hate doing this stuff. 6 minus lambda times the determinant of this guy, so the determinant of that lower matrix. So that's 3 minus lambda times 1 minus lambda, then minus 1. Now you go to this one, and you ignore these, and you do the cross product of what's left. Well, that's a 2, but the second one is subtracted. So it's minus 2, so it's plus, minus, plus, and I'm gonna post an example where we do a 4x4 so you can see how you move through your matrix to do this. That's minus 2 times 2 times 1 minus lambda minus 1 times 1, which is minus 1. And then we do the third one, which is this guy. Now it goes back to positive. You ignore this and you just leave with these. So that is plus 1 times 2 minus 3 minus lambda. I like doing it this way, just because I can break it up into pieces. And this works. It's called cofactoring your matrix, and it works for 4x4. You do this, you get a 3x3, you then cofactor the 3x3. It just keeps getting a bigger, uglier thing every single time. But unfortunately, it's kind of the way you have to go. And then we'll talk about if there's any ways to simplify this. And then you just do the math on this. I'm going to leave this 6 minus lambda on the outside. We're going to do everything on the inside here. So this is minus lambda times minus lambda is lambda squared. There's no lambda over here, so we're going to go lambda squared. We get minus 3 lambda, minus 1 lambda is minus 4 lambda. Then we have 3 times 1 is 3, minus 1, so plus 2. I guess it's the first one. Now we go to the second one. This is an easy one because this is 2, minus 2 lambda, minus 1. So 2 minus 1 is 1. So this becomes 1 minus 2 lambda. So 2 times 1 minus 2 lambda. Then plus, this 1 is here, so this is going to simplify much easier. This is 2 minus 3 is minus 1. Negative lambda becomes lambda, so this becomes lambda minus 1. Now we carry this guy through. We get negative lambda cubed. Let's do our lambdas first. Actually, let's do the 6 first, then we'll do the lambda, just so we stay consistent. 6 lambda squared minus 24 lambda plus 12. Now we'll do the lambda piece over here. Minus lambda cubed plus 4 lambda squared minus 2 lambda. So this is all one term. Minus 2 plus 4 lambda plus lambda minus 1. Now we're going to combine terms. We only have a lambda cubed, so minus lambda cubed. Now the lambda squared, we have 4, and that is all. Is that right? Did I lose a lambda squared somewhere? Yeah, I did. Sorry, 6 lambda squared, 4 lambda squared, 10 lambda squared. That's what I was looking for. Now look at our lambdas. We have 24 here, negative 24, negative 26, plus 4, negative 22, negative 21. Yep. Am I off by 1? So this is like I did something wrong here. Yeah, I think I should have 23. Oh. Where did I lose my lambda? Let's lose some. Okay, that's minus 24. This is the problem, is you can lose pieces and it sucks. Minus lambda, 4 lambda, that's right.
This is too hard.
Oh, it sucks. It is miserable doing this. I'm not going to disagree with you. Now, there are equations that should help us solve this much easier, and I'm going to show you those ways to solve this numerically. But I just want you to see where this comes from. But you can see where the problem comes in. So that, let me just make sure. 6, that's minus 4, that's minus 24 lambda. So that's true. We have plus 2 lambda here, minus 2 lambda. So minus 26, that's right. Oh. This should also, -2 plus 4 lambda. That's right. Dude, this sucks. It really is miserable doing this.
Plus minus 21.
You're getting -21, see, and I had -23, so what did I do wrong? Well, let's call it -21 lambda, and then I'll figure out if I made a mistake.
Plus 9.
What's that?
Plus 9.
So we have 12, we have 10, we have 9. Okay, now assuming I didn't screw the math up, which is a possibility I did. Then let's talk about how we solve this. Let's do the technique we talked about. And then that'll wrap up for today. And then I'll show you next time the easier way to do this. Because this is miserable. There's no question. It is absolutely awful to do. But it's a necessary evil.
Can we do polymath this thing?
Oh yeah, you're more welcome to use polymath. Actually, polymath will do the determinant of a complex matrix on it.
Is it? I'm not sure. I never made
I would think it would.
matrix on polymath.
Yeah, we'll see. It should do it. MATLAB will do it also.
My left leg.
That's great.
MATLAB and MATLAB will do it, but
Five solutions on my left leg too, but not one.
21 is.
what's that?
It's 21.
21 lambda?
Yeah, 21.
That's what I thought. But I don't know why I screwed up before, so who knows? I don't know how I screwed up. Oh yeah, by the way, if you have a numeric matrix, it will do determinants of just numeric matrix. If you just use equals m determined, it's actually a matrix calculator, but it doesn't do variables. So let's say we have this equation now. We have lambda, we have -x squared, -x cubed, right? Plus, what did we say, 10x squared? Is that right? Yeah. Minus 21x. 21x. Plus 9, right? Equals 0. So this is our equation we're trying to solve. I know that's fine. I know you went, there, now I'll store it as a character. So this is the thing we're trying to solve. So let's go ahead and plot this and see what it looks like. Actually, because we're at 12 after, plot this outside of class. Or actually, if you don't want to, I'll plot it. We'll talk about it next time. We'll use solver to solve this, okay? It is ugly, and then I'm going to show you some ways to do this.
How much
That's not. It's a run through. Yeah. I think so.
You sure?
Pretty sure.
If you're using virtual applications in the future,
Can you put this
Ask Josh if you have any problem with that.